Well, today we're going to look at special right triangles, or if you're from Castile, especial right triangles. They're only special because they're particularly useful types of right triangles. The first one we're going to look at is actually an isosceles right triangle. Why not look at equilateral right triangles first? Well, I think the simple answer would be there's no such thing. It wouldn't work. See, if we had a right triangle with all equal sides, well, then we'd have that x squared plus x squared equals x squared. Now let's assume that x doesn't equal 0, because if it did, I don't see how we'd have a triangle. We just have a point. Well, this is 2x squared equals x squared. Now x isn't equal to 0, so we can divide through by x squared and get that 2 equals 1. Remember back when we studied different types of proofs? And one of them was proof by contradiction. Well, this is proof by contradiction. This can't happen. This can't happen. So, there is no such thing as an equilateral right triangle. So, the only thing we can do next is see if there's such a thing as an equilateral. Of course, I mean isosceles. In fact, I can tell you right now, it will work. Well, here's one thing that's kind of special about an isosceles right triangle, and they do exist. There's nothing wrong with that. This each has side x here, right? So x squared plus x squared is 2x squared equals h, or h equals root 2 times x. You can always say that when you have an isosceles right triangle, the hypotenuse is root 2 times x. That saves you a bit of arithmetic. You don't have to square these and add them up. Just square root of 2 times whatever this side is, or this side, doesn't matter. What else might we know about this? Well, this is a 90-degree angle, right? Yes, it is. The sum of the angles in a triangle is 180. Well, if this is 90, then we've got 90 degrees left over to divide up between two angles. But remember, back a chapter or so ago, when we figured out that the base angles in an isosceles triangle are congruent. And that's true for a right triangle. The base angle congruence theorem was true for all isosceles triangles, so it's certainly true for the special case of a right triangle. Well, we've got 90 degrees that has to be split up between these two such that these two are equal. Or, to put it in algebraic terms, we could write that 2 times the unknown angle, say alpha, equals 90. So, these two angles are both 45 degrees. You probably knew that before I worked it out. That's the other thing we can say about any isosceles right triangle. The base angles are always going to be 45 degrees. There's also the 30, 60, 90 right triangle. It's special because, again, you can quickly list the dimensions. If the short leg is x, the hypotenuse is 2x. And the longer leg, that's root 3 times x. Well, why the heck would any of this be true? Well, let's see. Suppose we take this triangle here and make this the bottom side. So this part here will correspond to this line right here. Once we've done that, we create a copy of it and put it right next to it, after flipping it horizontally, of course. Put it right next, so we have these two congruent triangles. When we put them together, what have we got? Remember, these are just two copies of our original right triangle. You could think of this one as the one over here, and then we made another one and flipped it and put it over here. Well, when we put this together, what do we know? Well, for one thing, we put the shorter side on the bottom, so we know that this is x, and we know that this is x. Right now, that's all we know. We don't know this yet. We're trying to figure out why in the world this would be true. Well, let's see here. This angle is 30 and 30, that's 60. But this angle is 60, and this angle is 60. It's equiangular. And we have a theorem that tells us that if all the angles are 60 degrees, it's equiangular, it will be equilateral. So this whole triangle that we created by putting a copy of this one right next to it is an equilateral triangle, which means this side is 2x. That's because this is 2x, of course. So they must all be 2x. But wait a minute. This is the right angle from over here. Remember, we just sort of flipped this up onto this side here. So this 2x here, that's an hypotenuse. Actually, that's the hypotenuse of a carbon copy of the triangle. You can look at it either way, but the point is, this is the hypotenuse, and it's apparently 2x, isn't it? Because it's exactly equal to the other sides of this equilateral triangle we created. So, boom, we can write 2x in here. But now that we've got this, it's pretty easy. Because this one here, let's call it y. Well, we have 4x squared minus y squared would equal x squared. Or, you can add y squared to each side and subtract an x squared, and we'll get that y squared equals 3x squared, or y equals root 3 times x, which is, that's what we had, isn't it? So these are, obviously they're laying this out for you because it's easy to remember, and I think they kind of expect you to remember this for the state exams. So the isosceles and the 30-60 right triangles are good ones to remember. For the isosceles, remember it's x, x, and root 2x. The two sides are x, and the hypotenuse is root 2 times x. For the 30-60, it's x, root 3x, and 2 times x. So now let's work some problems using these new facts we've got. Find the length of AC. Well, if this is 45 degrees, this is 90, there's only 45 degrees left over, right? Because they all have to add up to 180. That means we can immediately say this is 45. Wow. If I could write, we could say that. Okay, that's 45. Now, what do we know about a triangle with two 45-degree angles? We know it's isosceles. So this length, we don't know what it is yet, but they're both the same. That's x, and that's x. And we know that the hypotenuse in an isosceles triangle is root 2 times the side. So we have that 7 equals root 2 times x. Well, that just means x equals if x is 7 over root 2, well, how come I don't see that answer up here? Because they rewrote it. You'll see this a lot in this chapter. Instead of writing 1 over the square root of 2, like this, they frequently write root 2 over 2. These are the same thing. Why? Well, multiply the top and the bottom by the square root of 2. Square root of 2 times the square root of 2 down here is 2. And square root of 2 times 1 is square root of 2. So when you get this 1 over root 2, it's frequently rewritten as root 2 over 2. In fact, that's a pretty common expression. It's so common I can actually tell you exactly what the decimal representation of that is. It's 0.707. It's used a lot in trigonometry. So if I didn't say it explicitly, this is the right answer. 7 over the square root of 2 is the same as 7 times root 2 over 2. Now they want to know which one of these triples would not be a 30, 60, 90 triangle. Well, let's remind ourselves what the heck the dimensions of a 30, 60, 90 triangle would be. Remember, if we have a short leg equal to x, the other leg is root 3 x, and the hypotenuse is 2x. So this is the kind of triple we're looking for. For instance, here we have 1/2, root 3 times 1/2, and 2 times 1/2. That works. Here we have root 2. Well, root 3 times root 2 is root 6, and 2 times root 2 is 2 times root 2. So this one works also. What about this? There we have 5 over 2. Remember, the first one's arbitrary. It's the second two that have to match up with this. So this one has to be root 3 times 5 over 2. Well, it is. And this one has to be 2 times 5 over 2. And I don't think it is. 2 times 5 over 2 is 5, and they got 10 here. And let's double check. It looks to me like the answer is going to be C. But over here we have 3. Root 3 times 3, and then 2 times 3. Okay. This is the one that doesn't represent a 30, 60, 90 triangle. Or how about just a 30, 60 right triangle? Okay, here we have a couple of problems that the mailman tried to work out. Came close. We have the short leg here in a 30, 60 right triangle. If this is 30, this one must be 60. That's all you need to know. You only need to know one of them. The other one's automatic. Well, what do we have? The short leg. The longer leg is root 3 times the short leg, and the hypotenuse is 2 times the short leg. Well, he's got the hypotenuse as what should have been the leg. In other words, it should have been root 3 times 7 here, and then 2 times 7 here, or 14, of course. Though he just got his hypotenuse confused with his longer leg. What about this one here? Well, this is root 5, and this is root 5. Well, for an isosceles right triangle, the hypotenuse is, if this is x, the hypotenuse is root 2x. So if this were x, then h would be root 2 times x. Well, if root 5 is x, then it should be root 2 times root 5. Or you could probably write it as root 10. But you should have been a square root in front of that 5 there. It should have been like that. So this one was, well, they used to say close but no cigar. I don't know what they give out now when you get something right. An e-cigarette maybe? So it's close but no vape. Well, for this, first off, remember, maybe you do remember, but radical means that little thing. That's a radical. And that means square root. If you put a little 3 up there, I think that means cube root, and on and on. There are easier ways to write it. Maybe you've seen the notation in algebra where if you wanted to write the cube root of x, you could just write x to the 1/3 power. I don't know if you did that in algebra last year or not. It's usually easier than this, but at any rate, this is the radical. It has nothing to do with politics. It doesn't mean that this is they don't want it in a far left liberal form. They mean they want this thing here. So it looks like what we have here is two 30-60 right triangles. How do we know we have two? Well, we know we got one. This is 30, that's a right angle, so this has to be 60. No way around it. What about these angles? Well, remember, this is, no, these are perpendicular and these are perpendicular. That means that these two lines are parallel and these two lines are parallel. So we have a rectangle, in other words. So this angle and this angle, these are opposite interior pairs, right? So this must be 30. And that means this has to be 60. And it's a right triangle here. So we have a couple of 30-60 triangles. All we have to do is figure out F and G. Well, this is the long leg of a 30-60 right triangle, which means that 10 equals root 3 times G, or G equals 10 over root 3 . And to put this in simplest form, they like to get the radicals out of the denominator. I don't know why. It's perfectly legal to do it this way. I mean, that's a legitimate number. Plug it into your calculator, you'll get a number. But usually they put the radicals up in the numerator. So all we have to do to get rid of this is multiply the top and the bottom by root 3. So we get 10 times the square root of 3 over 3. Well, that's what G is. This is the short side. And for a 30-60 triangle, what's F? Well, that's the hypotenuse. And that's just 2 times G. Well, 2 times this, if we, let me do it over here. We got 2 times G equals the hypotenuse, which is going to be 20 times the square root of 3 over 3. Not too bad. Well, they're not supposed to be bad. They're supposed to be easy. That's the whole point of remembering 30-60 triangles and isosceles right triangles. If it didn't make things easy, then what would be the point? Well, they want us to find the coordinates of A in this one. That's right up here. And I think the easiest way to do this would be to draw your little altitude from the hypotenuse to the right angle, because we know about the point where that altitude crosses the hypotenuse. We're going to call that D, right? So then we know that we've got some ratios here, that CD over AD is the same as AD over DB. There are other ways. I mean, previous chapters we would have tried to find the slope of this line. We know one point on the line and the slope, so we get to find the y-intercept. That would give us the equation for this line. The slope of this line is the negative reciprocal of this one, because it's perpendicular. So we could set up that equation and find the y-intercept. Then we would set those two equations equal to each other and find where they intersect right here at A. One problem: we don't have a slope. In other words, we can guess that this is pretty close to 1, a little bit more. So the rise over the run would be 1 over 2, but it's a little bit more than 1 over 2. But that's kind of a crummy way to do it. As long as we have this, our theorems about the altitude and how it breaks things up. Let's try that and see what we get. We still have to eyeball this part right here, where it looks like it's right halfway between. So this length here is 3 plus 1.5. Should be 4.5. Or now let's write our equation first. That we've got CD over AD is AD over BD. That's this small section over here. Now that gives us that AD squared is CD times BD. And this is where we just eyeball it and say that this is 3 plus 1.5 is 4.5 here. 9 over 2. And what's left is 3 over 2. That gives us 27 over 4 for the length of this here. Squared, actually. So we have to take the square root of 27 over 4. And we can put down here that AD equals, well, the length of this is about 2.6. But they ask for the coordinates. Well, we're down here at y equals -1 already. So if we go up 2.6 units, that means y is going to be 1.6 right here, doesn't it? Just 1 less than the actual length. And why is that? Well, this is a vertical line. Remember? Our altitude, since this is parallel to the x-axis, this is a vertical line parallel to the y-axis. So we can use the length of this to figure out what the y-coordinate is. If this was at any kind of an angle, we couldn't do that. But we're lucky. It's just straight up and down. So all we have to do is take the length, subtract 1 from it, and that is our y-coordinate. Our x-coordinate, well, we already decided that this is halfway between. So that's 1.5 or 3/2. So for coordinates, we should have gotten 3/2 and 1.6. Or to put it in the same terms, it would be 1.5 and 1.6. Here we have one where they're asking us about the height of a ramp that's used to launch a kayak. They say this ramp here, the slanted part, that's 11 feet. And they tell us that we've got a 30-60 right triangle. So we have that the hypotenuse, 11, equals 2 times h. That's because h is the short leg here. This is the long leg. This is the short one. Or, so we get h equals, well, instead of writing it that way, let's just write 11 over 2. I was going to write 5.5, but 11 over 2 is probably a legitimate answer. If you don't like that, you can write 5.5. They're both right. Again, just had to recognize your 30-60 rule. And somewhere along the way, you may hear of an 80-20 rule. That has nothing to do with geometry. The 80-20 rule is that 20% of the people cause 80% of the problems. If you ever go into management, keep that in mind. 20% of your employees will cause 80% of your problems. If there is such a thing as a problem in school, and of course I know that schools never have any problems, but if there were, 80% of the problems would be caused by 20% of the students. Unless, of course, the problems were caused by teachers, in which case 20% of the teachers would be causing 80% of the problems. It's an interesting fact. For instance, if you're on the road, that means that since 20% of the people are creating 80% of the infractions, the same people who are running red lights are also running stop signs, speeding, ignoring school zones. They have to be committing more than one infraction per person, since those 80% of the infractions have to be spread out over only 20% of the population. So when police say that they write people up for fairly minor tickets because it discourages them from the other more serious infractions that they are sure they're committing, statistically they're right. I know it sucks because nobody likes tickets, but the fact is, if you're doing one of those things, you're probably doing a bunch of the others too. That's the 80-20 rule, and it has nothing to do with geometry. Well, here's one that's not too tough. Show that all isosceles right triangles are similar to each other. For instance, I've got two here. They're both isosceles right triangles. And I want to be able to show that they're similar. Well, let's see here. This is a right angle. And these are both 45-degree angles. This 45. This 45. And of course this is 45 also. But we have an angle-angle theorem, which says that if two of the angles are congruent, then the triangles are similar. What about this side here? Well, if this is x, and we'll say this is y, what is the relationship between x and y? Well, we can always write that y equals k times x. That's no problem. After all, you want to know what k is? It's just y over x. Multiply this side by y over x, and you'll get this. Multiply this side by y over x, and you'll get this. Which means that you can always say that these two sides are in the same ratio. That is to say, this side to this side and this side to this side are always going to be in the same ratio. And that's kind of obvious, really. I mean, you've gone from x to y here and from x to y here. Whatever your scale factor is, it's the same both times. So we have two sides that are in exactly the same ratio, and the containing angle, they're congruent also. So we have our side angle side theorem. So the two ways were the angle theorem and then the side angle side theorem. Well, this stuff was all fairly simple. I'm sure you didn't have any trouble with it, and that's about it.